Hi, my name is Aryan Arora. I'm a junior and I'm from Houston, Texas. And so my project is basically about investigating the viability of atmospheric water generation. So before we get into the specifics, let's talk about what this even means and why this topic is so important in the first place. Well, in many areas across the world, people have minimal access to clean water for their daily uses. And this is because freshwater faces pollution in the environment through numerous different ways, including mining activities, pesticides, poor irrigation practices, and industrial waste. And there isn't enough funding to purify water across the world. The main commercial methods of producing and purifying fresh water include reverse osmosis systems, which force water through a semi-permeable membrane, and UV sterilization filters, which use UV light to destroy contaminants. But these methods can cost a significant amount of input energy and hence money, which isn't always feasible. So we're looking for a better alternative method. And that's exactly where atmospheric water generation comes in. Atmospheric water generation is basically a process where clean water is directly condensed from the moisture in the air. And it's useful because it could be implemented in remote areas to supply safe drinking water and possibly cost less money and energy. So in this project, we're trying to assess the viability of atmospheric water generation. There are numerous technologies of AWG, and we're looking for the best sequence of them to produce maximum efficiency and economic viability. And so I theorized that this specific sequence, which is a dehumidifier, basically the opposite of humidifier, coupled with an evaporative cooler, which is a device that evaporates water to cool air, provide the most cost-competitive clean water by simultaneously purifying water and providing air conditioning. And so I built a prototype device to test out my theory, and this is its design. Well, right here, you see you have this 6-inch diameter fan. Over here is this plastic rectangular container. Right here is evaporative cooler pad. These are copper refrigeration coils. There are three DHT22 sensors which measure temperature and humidity over here, and over here. This is an Arduino microcontroller. This is a relay switch which controls all the devices. This is a power source. These are two collecting reservoirs underneath my system. And these are two DC fountain pumps over here and over here. And so this system works in a specific manner. Well, ambient air from a fan is passed through a wet evaporative cooler pad, which humidifies and cools the air, making it reach high levels of relative humidity. And a container filled with water is then placed underneath the cooling pad. And a DC pump placed in the container pushes water through vinyl tubing that runs over the pad, dripping water through the holes and back into the container. And this is what makes the pad wet, basically. And the humid air then passes through an evaporative coil filled with ice cold water, which causes condensation in the humid air onto the coils by lowering its temperature and making it reach its 100% relative humidity, or its dew point. And the condensed water is collected in a vat underneath the system. The ice water flowing through the coils is also powered by a DC pump between the coils and an ice cooler. And then the temperature and humidity of the air are recorded at three different places in the system by tiny DHT sensors. And those are in three different places, which are before the sponge, after the sponge, and after the evaporator coils. And then all the electrical components of the system, the fan, the two DC pumps, and the DHT sensors are all connected to and powered by the Arduino microcontroller. And so yeah, that's my design. And like right now, I'm working on a research paper about my findings. And my results so far have not shown they've shown a proof of concept and that the technology produces water, but it's not like that efficient yet. And so my future plans are to conduct more experiments to collect data and also change variables to try to increase efficiency. And then I'll compare the efficiencies to commercial systems with the same controlled variables in order to analyze the economic viability. And so, yeah, that's my project so far. Thank you for listening.